Machine Vision for Visually Impaired People, Chapter 6, Hand Detection, Part 1. These videos about hand detection are going to be the first in which I'm going to make passing references to math and to image processing functions. In this series, we're gently sliding down the slippery slope of technology talks, and we're just going to pick up speed a bit here. So now in the point and speak beta, and currently in 2 features of the Echobatics app, we have together merged optical character recognition, OCR, and hand detection. It's going to take me a couple videos to cover topics related to hand detection. We're going to talk about image formation, skin tones, and also machine learning models and other statistical techniques for hand detection. In the Echobatics app, Explore mode reads text at the end of the user's finger. In read mode, text is read on an object in the user's hand. So it could be a label that extends beyond the user's hand. And we want to read just that label, not things in the background. For hand detection, we typically want to distinguish between the user's hand and everything else. The hand, the object to detect, is the foreground. Everything else is the background. That includes visible skin of the arms, the feet, and the face. It's noise, stuff to be ignored, even if the hand is directly in front of skin of the same color. In order to talk about the relative size of the hand in an image and how that's relevant to hand detection for actual practical applications, I need to talk about perspective projections, or the apparent change in size of objects as they are nearer and farther. And I'll mention again that as a consequence of the misalignment of my eyes, strabismus, which is also a condition that's common for people who are blind or have low vision. So I'm stereoblind, and I see the world in a way that's very similar to the way that a smartphone camera sees the world. It's flatter than typically sighted people see it. I don't know exactly the difference because I've never experienced vision the way typically sighted people have. Partly as a consequence of my vision, and also because of my work in machine vision and computer vision, it's slightly more obvious to me how weird vision really is. Now, I do perceive depth based on shadows, focus, out of focus, and in particular, based on the relative apparent sizes of objects. And that's what we're going to talk about in this video, because a hand detection algorithm or machine learning model could in fact detect feet, tiny plastic hands, hands that appear in printed images on brochures, hands in reflections from shiny surfaces, or hands of a somewhat distant person rather than the hand of the user. So that's why this is the first video in which I'm going to talk about image formation, and I'm going to talk about the relative sizes of objects in images and perspective projections. Now, we live in a world of 3 dimensions, but a camera or a single eye forms an image of 2 dimensions. A digital image is just a grid of pixels. Pixel is short for picture element. And each pixel has just one color. An image is a little bit like 1-by-1 Lego bricks attached side by side on a large Lego sheet. Each Lego brick can have a different color. The apparent or visual size of an object depends on the distance from the eye or camera to that object. At twice the difference, the object will be half the size. In computer vision and machine vision, and if an object like a hand occupies too little of an image, now I'm going to move my hand close so it occupies much of the image, and as I move it farther and farther away, it's occupying less and less and less of the image. If a hand, as detected by a hand detection algorithm or machine learning model, if a hand is too small, you may want to ignore it. In fact, you probably should, for reasons that I mentioned before. It could be an image of a hand. It could be a hand of someone other than the user. I want to describe briefly this effect of apparent image size changes in a way that I hope makes sense to people with little or no vision. Recall this series is called Machine Vision for Visually Impaired People. So here are two ways to describe how the apparent size of an object changes in an image as that object gets closer or farther away. Sound shadows. Visual size varies like the apparent size of a sound shadow. So if you imagine that there's a tall, skinny building between you and a street full of cars, and you are initially far from this building, the sound shadow will be relatively narrow. And for those of you who have training in orientation and mobility, O&M, this will be a very familiar example in your everyday life. So far away from the building, the sound shadow is narrow. As you get closer to the building, the sound shadow gets wider and wider and wider. Similarly, a visual object blocks the view of what's behind it. As you get closer to this object, which could be a hand, which could be another person, which could be a building, it occupies more and more of a sighted person's vision, or of a camera's field of view, what the camera can see. Your hand, as it gets closer to or farther away from a camera, occupies more or less of the image. Think of it as a narrower or wider sound shadow. Next example, angled arms. So if you're familiar with analog clocks, minute hand and hour hand, think of holding your arms at roughly the 10 o'clock position and 2 o'clock positions out away from your body. So your left arm is at the 10 o'clock position and the right arm is at the 2 o'clock position. Or if you want to think in terms of compass directions, imagine you're facing north, or actually face north, and your straight left arm is pointing northwest and your straight right arm is pointing northeast. So that angle between your arms approximates a sighted person's visual field. It approximates the field of view of the camera in your smartphone. Close up to your body, what a sighted person sees spans the distance between your shoulders. At arm's length, vision covers the space between the fingertips of your two hands. If you've played goal ball, this will hopefully make some sense. So imagine a goal ball, which is roughly the size of a basketball. Imagine it between your outstretched arms. It's somewhere in between there in space. Now, if the goal ball is close to your body, then that ball occupies most of the space between your shoulders. That's like a ball that's close up to someone's eyes, occupying most of their vision, if they're sighted, or most of a camera's field of view. Now, with that same ball located a distance from your body that is the same distance as the fingertips of your outstretched arms at the northwest and northeast positions, that ball occupies maybe half to a third of the space between your fingertips. Similarly, that ball occupies maybe a half to a third of the width of a sighted person's vision, or the horizontal field of view of a camera. Now, how relative size is relevant to hand detection in images from a camera is this. Hand detection can detect a tiny plastic hand or a tiny image of a hand if they're close up. That tiny plastic hand or that image of a hand could be confused for the user's hand. If other people are standing in view of the camera but farther away, their hands may be smaller in appearance, but their hands are likely to be detected by the same algorithm or same machine learning model that can detect the user's hand. What this all leads to is this. For hand detection, you'll want to filter out hands that are too small or too large. The hand size in the image depends on the distance from the camera to the hand and also the size of the hand itself. But if you filter out hands that are too small, that's going to improve the robustness of hand detection in a variety of scenarios. In the next video, I'm going to talk about skin tones and foreground-background discrimination, which in image processing, we also typically call segmentation. Thank you. Feel free to contact me. Go to echobatics.com.